The robot learning has been like a pretty hot topic recently in the past 2 or 3 years, ever since LLMs. And what robot learning is about is essentially applying these learning-based methods for robotics. And today we'll be covering robot foundation models. So these are foundation models specifically for robotics. So we handpicked sort of 3 papers. I'll be presenting the Pi0 paper, which has been pretty foundational. And then Krish is going to present the TRI paper. And then we'll do a third on Gemini robotics. And so these papers that we picked out are sort of like really state-of-the-art. They just got published like this year and last year. I decided there was like an older paper, for example, RT1, RT2, RTX. These were like the first robot foundation models in 2023. But I decided not to choose them because I want you guys to know about what is the state-of-the-art. And we'll be covering state-of-the-art today. I mean, Pi0 is slightly older. There's been Pi 0.5 since, which we could potentially cover next week. But first, we're going to go with Pi0 and just give you an explanation of what the paper is about. Assuming you guys kind of read it, I will go a bit deeper into some details of the paper that I think is interesting. And then what I hope is we're going to have some interesting discussions, some questions, and I don't want to be the only expert here. Like I would love to have some people who also have a deeper understanding, and have some back and forth, so we can have discussions and think about, we want to work towards a day where we have robots in our home, and I think the way to enable that is by having these large foundation models, or maybe there's some other way, but think towards that direction. Any questions so far?
You're okay with dumb questions, or you want smarter questions?
I think you can ask any question, okay. Because if you have the dumb question, probably someone else also has the same question. Yeah.
Why should I listen to you?
Oh, why should you listen to me? Honestly, that's a great question. Why don't you just go out there and listen to Sergey or Chelsea Finn, who are more, I guess, knowledgeable than me? I know I would also argue that I would not listen to myself. But I would argue what we're doing here is not as much, I'm not totally trying to position myself as an expert. I want to create a space for all of us to learn, because nobody here, there's not that much there's no robot learning basically going on at Waterloo. And me personally, I am working towards being much more knowledgeable in this field. And I just want to start creating the space. And I did spend a summer working on robot learning, and I've been reading a lot of papers. So I would say I'm not a total noob. And I spent some time reading this paper and trying to go deep in it. So I would say, compared to the average Joe, I probably know a bit more. But yeah, I'm still learning. If you think you're in a better position, I'm joking. Okay, cool. So we're going to go over Pi0 first. So this paper was released around, I'd say, fall of 2024. And it was created by a company called Physical Intelligence. So first of all, we can go over, I think they have this blog page, which we can go over. And so with this paper, I guess there's 2 big contributions. They introduce a new architecture, and they sort of show how they leveraged lots of data to train this. And at the end of all of this, they were able to train this sort of generalist policy that was able to complete lots of different tasks. So you can see it do laundry. It also did cardboard folding. So yeah, just a bunch of different tasks. And this paper sort of explains how they were able to do all of that, right? And I guess we can preface, as I mentioned briefly before, this is not the first robot foundation model. It was released in 2024. So they have some baselines. The main one that they compare against is OpenVLA and Octo. You guys can read these papers. I think I linked it in the description. Right? So Octo was also created by Chelsea's group. And then OpenVLA is an open source vision language action model. I'll briefly explain how OpenVLA works to give some context on why Pi was designed in the way it is. But just hold that thought for a second. Let's first go over sort of how is Pi, how does the architecture work? And one thing that's interesting to mention about these robot foundation models is that if you read the paper, you'll see that this robot foundation model was actually trained on lots of different robots, right? So you can imagine these are sort of all the different robots that are trained on. So you have some ARX arms, UR5 arms, Francas, and you also notice that they have single arm setup and bimanual setup, right? And you might be wondering okay, why do they want to do this, right? Because you can imagine, right, you have a policy and then okay, sometimes it's got to work on the Franco arm, sometimes it's got to work on the ARX arm. Like, isn't that, if you train on all these different robot embodiments, isn't that going to give it brain damage? So there's that side of the argument. But generally, as we see the trend with robot foundation models, they like to train on all these embodiments. And the intuition is that perhaps by forcing it to like see all these different embodiments, it can sort of like learn things that will enable it to generalize better, right? So like, if the policy needs sometimes to work with an arm that like doesn't work as well, or like different, there'll be different action representations for each robot arm. Sometimes you only like want to operate one arm. Sometimes you have to operate both. And by having to do this, maybe it can increase a robot's generalization abilities. And so that's what they did here in their pre-training mixture. They'll sort of mix all of these different arms. But yeah, before going too deep into that, I want to just go over the model architecture. Right? So if you look at the paper, this is sort of the architecture that they've decided to go with. Right? And so they'll use this pre-trained VLM, which is PalyGemma. And PalyGemma was, it's a model released by Google, and it's a vision language model. So this was a model that it takes in images and it takes text, right? And then what it will output is just text. So in the original PalyGemma paper, it kind of looks like this. It's actually quite simple. You take an image, you take a text, right? So here, the image is some image of this, and then the text will be where is the photographer resting, and then it will train to output text. And this VLM is again built on top of an LLM. So you sort of have these three layers. You have your base LLM, right? This your language foundation model, and then VLMs. What they'll do is they'll take your pre-trained LLM, and then you want to add image, and so they'll add this vision encoder, and this is actually trained separately from the LLM. This is a pre-trained vision encoder that comes from SIGLIP, and SIGLIP is also something else. SIGLIP is built on top of CLIP. So what this does is actually they'll take an image and text, and then you have two encoders, and then they actually train with contrastive loss. Okay, this is like minor implementation detail, but what you really need to understand is just, okay, it's a VLM, they just added this encoder so that the text can sort of like be represented in the same space as text, because this is what your LLM doesn't understand images. How do you make it understand images? You sort of like go through this encoder so that in some latent space, these embeddings can capture some like representation of this image, and then there's some like gap between what this encoder understands and what this decoder understands. So you'll do some linear projection. It's like, let's say your transformer decoder, your LLM only understands English, and this is like in German. Right? There's some gap between like the German and the English, and this is sort of like a mapping to go from German to English. Is sort of like how you can think of this. So that's your VLM, right? So far nothing has changed, nothing about robotics. So what they did is they take this VLM, and they'll introduce an action expert, okay? An action expert. So this is sort of one of the core contributions of this paper. And remember I talked about OpenVLA? So this is another sort of a vision language action model, robot foundation model, another VLA. So traditionally what people were doing is not do sort of this action expert as a separate model. What they would do is they would simply introduce, like if you think of the LM, right, it outputs tokens. What you could do is like, okay, you want to make it work for robots? What you could do is, I'm just going to take the let's say the least used tokens in language, right? The least used 256 tokens, and you're going to say each of these tokens represent a particular robot motion, right? So let's say like this motion of moving 0.1 meter to the left, that will represent a particular motion. So that's exactly what OpenVLA, one of these older models, would do. And then it would just train, like the VLA would be trained to predict these tokens, right? So it would work in a discretized space as opposed to a continuous space. This paper, what they'll do is they actually predict continuous action space. But they will introduce this action expert. And so this is where, for me, it got a little confusing. Like, so how do you get a VLM and action expert working together? Like, is the output of the VLM fed into the action expert? Like, how does this work, right? Because you see that they put side by side. And I think this is where it's kind of interesting. So I sort of like drew a diagram to sort of understand how this actually works in my head. So within your VLM, right, you have like these transformer blocks, and there's like 18 layers of them. right? So your VLM and your action expert actually run side by side, right? But there'll be this causal block attention between each layer. And what that will do is it looks something like this, right? So what you want is the expert, what this enables is the expert to attend to information that comes out of the VLM layer, right? So the VLM, all it takes in is image and text, right? And it's going to output image and text tokens in some latent representation. And same for action, but action takes in an action chunk and proprio. Proprio is short for proprioception. It is essentially sort of like the state of your robot, right? So your robot, say, has 7 motors. Each motor has some measurements. That's your proprio state. Action is like what you actually want your robot to output, right? You'll see like it takes in Gaussian noise. So it takes something, and we're going to explain this will be needed for flow matching, which we'll cover in a second. But back to how sort of like these two run side by side. You have your VLM and you have your action expert, and so in the original, so like their diagram, right? They have them side by side. But if you dig deep into what is actually happening, they sort of run side by side, and at each layer, they will have this causal block attention. And so you essentially, your action expert, you give it the ability to attend to tokens that come from your image and your text, right? And so after you go through your causal block attention, you still hear like these are just VLM tokens, but your action expert, right? There's still action and proprio tokens, but these tokens have attended to the VLM tokens. And you'll notice the text and image tokens cannot attend to proprio action. It's like similar to self-attention, where you can only attend to things in the past. But in this context, it's more like action can attend to image and text, but image cannot attend to action, right? So you imagine you have this model, you do your forward pass, and after you do your back prop, right, these weights can still change and affect the output, right? Because now your action attend to your VLM tokens. So if you change the weights of your VLM tokens, or the weights of your VLM, then it can affect the output. So in the back prop, as you update your model, the VLM weights will still, like they can change, right? Because they affect the output. But I think what's interesting is sort of you limit, like the information can flow, but only through this layer, right? So as opposed to like having the action expert baked into the VLM, they have like this separate module, and then they can only sort of like talk to each other through this attention layer. So I think that's quite interesting. In practice, this VLM is 3 billion parameters, and the action expert is 300 million parameters, making this a total of 3.3 billion parameter model. And how this is actually implemented, this is just Gemma, right? So remember we talked about PalyGemma, which is the VLM, which has the vision encoder, and just Gemma. This is just Gemma, but it's a smaller version of Gemma that's 300 million parameters. And so that's all there is to it. Right? The architecture is actually quite simple. Right? We've just taken a PalyGemma, and we've taken Gemma. And the one last thing that, in terms of the architecture side that's interesting, is how they do sort of like this action generation. And I think it's super cool. It's something called flow matching. And to give you some motivation of how flow matching works, I took this image. This came from the diffusion policy paper. So has everyone heard of diffusion? So diffusion, we actually took the idea of diffusion and we applied it to robotics, right? And the motivation for this is, let's look at this example, right? So this is a task where we have to take a block of T, and we need to start from here and push it to the green side, right? So that's our target. And you can see that the correct trajectories that we're learning from, there's actually 2 of them, right? Or like 2 modes of them. So either you can go around to the left and push it in, you can go around to the right and push it in. And so if you don't do diffusion, what might happen is, right, because when you're trying to learn these 2 trajectories, and you're trying to, like traditionally without diffusion, right, you're trying to minimize like your mean squared error, right? So you might end up just learning an average of those 2, right? Because sometimes the trajectory goes around like this, sometimes it goes around like this. So you end up just like learning the mean of those 2. But if you learn the mean of those 2, like it doesn't work. Like you can't just like go to the T. Like you actually need to understand that there's sort of these 2 modes. And so that's where diffusion is very, very like good for this. Diffusion and flow matching are like very, very similar. but they're really good at capturing these multimodal distributions. By multimodal, I mean not different like modalities, but rather two modes. So a distribution, let's say a distribution is like this. There's two modes, like these two other modes, right? And so yeah, this is why diffusion and flow matching are really good, because they can learn these multimodal distributions, which you might encounter in robotics. And so how does flow matching work specifically? It took me some time to like internally conceptualize this, but I'm going to try to explain how flow matching works from my mental model. So you can imagine this is our target distribution, and this is our source distribution, right? So we want to get to here, right? And this is sort of like a two-dimensional view of your distribution. So there's two modes here. Like this is very common, and this is very common, right? And we want to like get to that place. How do we get to that place? We start from noise, right? Because we can always sample from noise. So in practice, our noise comes from a Gaussian distribution. Has everyone taken like a stats course? Like a Gaussian distribution essentially looks like this. So most of the time you get zeros. Sometimes you get like 0.1, 0, or minus 0.1. But most of the time you get zeros. Like it's a way of modeling. It is a distribution, and it's the most common distribution that you'll end up seeing. And we know how to sample from a Gaussian distribution, right? So that's how we get our noise. And what we want to learn is how do we get from our noise to our target distribution, right? Our target distribution is this action, right? And so one way is through this flow matching step where you can imagine I'm here. I want to get to there. But sometimes I also want to get to there, right? So what we're going to learn, as opposed to like, OK, I need to, as opposed to learning, let's say, like a distance vector to those 2 points, we're going to learn like the velocity field. So you can imagine like, maybe an analogy would be you're in a river, right? And you're like starting from noise, and you're letting yourself flow to your target distribution, right? So what you want to learn is this velocity field, right? So sometimes you end up here, sometimes you end up there. And I drew these red dots over here because when they do the training, sometimes they're going to take this point, and sometimes they're going to take this point, sometimes they're going to take this point. So if the velocity vector is like this, you just sample some of these points along the trajectory. But the thing you learn is always this velocity field. So if you look at the paper, their flow matching loss, what the policy is going to predict is that velocity field. And then the ground truth is what I've described. It is the difference between your original noise and your target action, right? So you learn this, and then at inference time, what's going to happen is we're going to do like a forward Euler integration. So if you go back to my image, right, at inference time, what we're going to do is we're going to sort of like walk alongside the vector field, right? And you might be like, why don't we just like do one step, right? Because remember, if we did one step, it would sort of like learn the average of these two vectors, in which case you just like go straight like this, right? But we want to sort of like capture the multimodal distribution. And so as we walk forward, at first, it's like somewhere down the middle. But hopefully, the thing we learn will sort of like carry us to one of these two modes. And so that's the idea of flow matching. And so the equation looks scary, right? But really, it's a simple idea. We start from noise, and then the delta here is 0.1 if they do 10-step, right? And you should like slowly walk down your velocity field. And you repeat this process until you get to tau equals 1. And that is essentially how they do flow matching. So at the end of it, you do this 10-step flow matching. You use your VLA, this architecture. You do your 10-step flow matching, so you keep feeding in the action 10 times at inference times, or however many time steps you want. And then you get an action chunk at the very end. And that is essentially the architecture. Later on, we'll see like when we talk about some of these other papers, for example, the Gemini Robotics, they don't do this. So I thought it was quite cool that actually a lot of, if you look at the diffusion policy, or diffusion for robotics is quite a common idea nowadays. But this is flow matching, which is also very interesting. If you were to ask me the difference between flow matching and diffusion and why they don't use diffusion, I don't have a very good answer, but if someone has the answer, I'm happy to hear it. But if you look at literature, yeah, some people, the TRI paper, for example, uses diffusion, I think. But yeah, here Pi0 uses flow matching. And I guess finally, like, okay, we have all of this. What is sort of the performance we get? It sort of like does pretty well compared to OpenVLA and Octo. And the paper did cover sort of like the recipe. So okay, you have this really powerful architecture. How do you feed it data so that it learns correctly? And I think like there's not too much detail in terms of like how they did this. So they use a few data sets. There's like Droid data set. There's the X-Embodiment data set. So these are all just like robotics data sets. And then the VLM, right, they took, that VLM is already pre-trained on like internet data. So this is how they're able to, if you look at like, in the paper they say, oh, we have the Pi data set, internet pre-training, and X-Embodiment. So this is just taking a VLM that's pre-trained. That's how you get this. And these are just like robotic-specific data sets that you'll use to feed into your model. So you take a sample, you take like trajectories, it'll have image, it'll have text for like what is the actual task, it'll have the proprio state, so the joint measurements, and you sort of like, you know your ground truth action. And at training time, you just like feed in noise, feed all of this, do your flow matching loss, run this for a while. And then they also do fine tuning. So in robotics, it's very common to sort of like you do your, in like large language model in general, in LLMs in general, you do pre-training, and then you want to fine tune on like so that it like works with instructions, right? Or like you want it to have a certain behavior, so you'll fine tune it. So similarly, we have the same paradigm in robotics. But yeah, they have pre-training results and they have fine-tuning results. But I didn't think that was the most insightful part of the paper. Yeah, I just found the architecture to be pretty cool and interesting. And I think that's mostly it. There's here some fine-tuning results, but you can read through this. But essentially, you can see as you fine-tune, right? So you give it extra data specific to a robot station, right? Because the pre-training is like you have a bunch of robots, but now I want it to work super well for this robot at this station for this task. So you're going to give it like data specific to the station. So this is what they do. They fine-tune it, and it'll work somewhat better. You can go see here like goes from like about 55% to 80% after 5 hours of fine-tuning data. But I'd say there's still like many open questions. So after reading this paper, also here's like some, if you're curious about like real-time performance, right? Because a lot of these models are quite big. So how does it look if you were to can you actually deploy these and have them be useful? And I'd say like, yeah, 3.3 billion parameters is like tolerable. And it's around 86 milliseconds based on what they've shown on an RTX 4090. And I'd say like the reason this works is because we actually work with action chunks as opposed to like predicting one action. If you look at OpenVLA, which is this older robot foundation model that I talked about, they actually only predict one action. So if you predict one action, then you have to like do it many more times. Whereas if you predict an action chunk, you predict multiple actions, right? So you sort of like give yourself time to query your model again, and then predict another action chunk. So you don't have to like query your model as frequently. And that's the way they sort of get around this latency issue. A lot of like robot foundation models actually do this. So yeah, these are, do you have a question? Yeah?
Yeah. So in the action expert, you keep saying it's a gemma, it's like the same layer as a gemma. Is it the architecture the same? Because I think, I'm not sure if I recall correctly, but in the paper they mentioned that they trained the action expert from scratch.
Yeah.
Different robot states. Like,
yeah.
Is it like, are you just talking about it's the same as gemma, as in like it's the
architecture is the same, but you don't preload the gemma weights.
Yeah, they're not fine tuning off the gemma weights. They're
yeah.
from scratch.
Yeah, but the VLM part is you fully load the VLM weights.
Okay.
Yeah. So yeah, that's like sort of an overview, and these were sort of the questions that I had after reading this paper. All right, so one thing I mentioned is like, yeah, it seems like the recipe is still a pretty open-ended question, right? Okay, so you have a pre-training and then you fine-tune it, but like how exactly you do that is not very clear. How much fine-tuning data do you need? So actually, Krish's paper next sort of talks about some of these, or like the different scaling laws. How much fine-tuning data do you need? Does pre-training actually help that much? Like some of these, like this paper sort of showed that yeah, you you need pre-training, but there's more papers that cover this. And then I think the main thing for me is like, if you think about how this model is trained, right? Like LLMs in general, right? You have a large corpus of text on the internet, and you try to learn to like pattern match, like, oh, they talk like this, I'm gonna try to like talk like the way the internet talks, right? And similarly in robotics, we call it imitation learning. So it's like I have some expert demonstrations of how the robot should behave, and then your policy tries to learn that, right? But that could be very limited, right? Like imagine every time you go to a new place and you want your policy to work, you need to like collect new data, right? That's obviously not something very feasible. In context learning is a really cool way to solve this, which the Gemini robotics paper does, right? So you can imagine like you have a model that's already trained, and instead of like actually making updates to your model, you just like give it as part of its prompt. You give it examples and context, and then it will just be able to work out of the box without having to update the model. That's a really powerful way of doing like making it work in new environments without having to actually update your model. And another way is like doing reinforcement learning, right? So you can imagine right now all of these expert demonstrations, they're human collected, right? The robot's not really learning from its own data. But the whole premise of RL is that you can have a policy learn from its own demonstrations, right? And the way it can learn is because there are the concept of reward, right? And it can know, oh, this trajectory is good or this trajectory is bad, right? And based on that, it can learn to optimize itself so that it can maximize the reward, right? So like, it's a very cool idea, but in practice, still RL is like really hard to get right. So perhaps there's some other ways. And yeah, I think those are the main questions. And now I think we should discuss if anyone has questions or like if people have different insights or things that they found interesting, we can discuss. Yeah.
Personally, I found the most interesting part of like, where the action expert and in the casual attention block. Mm-hmm. So like, in the original transform paper, like tells like how it kind of makes sense that semantically like the relevance to each token in the sentence determines which tokens are important, and that's what it uses. It gives it more like weight in a sense, and that's what the output is determined. But do you understand? Because I didn't really get that when I read the papers. Like, how does doing matrix multiplication between the action expert blocks and the VLM blocks result in better results for what actions to be?
Like why it works?
Like do you understand semantically why that? Because I personally didn't understand that. That's like I think my biggest problem I have with the paper.
I see.
Because
like why it needs to attend to images and text? Or?
Yeah, sure, like you just say that it works, right? But like
why does it work?
Like, why does it work mathematically speaking? Like do you know like attending to like different like the image tokens, image text tokens with the action tokens. So like and like multiplying those or like whatever it does, like how does it does it result in like better results?
Well, if you only had the action expert, right? All the action expert sees is the proprio state and this original like action noise, right? But like you need images, right? Like let's say if I just taught my robot to fold a t-shirt blind, right? Like it can memorize like how to do this and then fold it and then put it away, right? Yeah. But you want it to actually see what it's doing, right? Like if you just close your eyes and do it and like there's no t-shirt in front of you, right? Versus sometimes maybe you try to grasp your t-shirt and like you don't grasp it. You're gonna try again, right? And so that's why you need to have your action expert see. And also the prompt is also important, right? There's something called language conditioning, which is like you want to condition your policy on language. For example, if there's an apple and an orange in front of you, and you just run your policy, sometimes you want it to pick the orange, sometimes you want it to pick the apple. An image alone is not enough, right? And if you train, if you don't have it as a text prompt, right? And then like maybe sometimes you pick the orange, sometimes you pick the apple, like you want a level of precision, and language conditioning allows you to do that, right? So yeah, like I think because you have this attention layer, right? They don't feed the image directly into the action expert. It goes to the VLM, right, which is already pre-trained, so it's not from scratch, right? So it already like captures some meaningful representation of this image, and then you just let the information, the action expert can attend to the VLM. It'll know like, oh, maybe learn which tokens are important to learn, right? Like maybe the text is not that important. Like certain patches of the image are more important to learn. So that's why I think maybe a question would be like, okay, is there a point of an action expert? Like, why don't you just like put that in the VLM and introduce like new tokens, right? Is that perhaps the question?
Also, like, I guess maybe like it comes as more like how the decoder maybe interprets the whole thing. Did the paper talk about that much? Like after you get like your matrices at the end, right? After it goes to all this, I guess it makes sense a way of saying it goes to the VLM, and then they do attention between each other, and then it highlights important parts.
Yeah.
And then I guess like how does it decoder interpret that? I think that would be a good question. That I think. Do you know if the paper talks about that?
Like for example, I think in the original Transformer paper they talk about like the words, and you look at which words attend to which word, right? Yeah, I don't think the paper talks about that, but it'd be cool. I think so. This repo is open source, so you can run it and see. So like you can visualize this attention matrix and then see like which tokens attend to which. So I don't think they did much analysis on that, but you could, yeah. Yeah.
So the action expert layer and the VLM layer, are they all decoded into tokens, I'm guessing? Because I'm wondering how they like be concatenated in the attention block, because they're very different modalities, right?
Yeah.
So how are they represented in the attention block?
Yeah, so actually the VLM layer is the sort of like hidden dimension is 2048, and for the action expert, the hidden dimension is 1024. So they have actually different hidden dimensions, and yeah, I was confused on like how you can just like merge them, right? Yeah. It's because like if you look at my understanding, right, maybe it's like slightly wrong, but my understanding is that right before you do the attention, because the attention is you actually do like multi-head attention, so you'll split into different heads, and when you go into each head, there's actually a projection matrix, and when you multiply by the projection matrix, maybe I have a visualization to do this. Transformer. This is my best mental model of like how it works, right? So this will be just your traditional transformer, right? And let me close this. So in this case, you tokenize. All right, so you take from your embedding matrix, you have your input embedding, apply some positional encoding. There's some layer norm, right? But the attention is here, right? So the row is sort of like each row represents a particular token, right? And then the column length are like each row is a token, and then this is like the hidden dimension, right? And when we do attention, we sort of split it into different heads, right? And so it looks something like this. And so when you multiply, so the Q, it's given by your input multiplied by WQ, right? And so this WQ, here I made it D by D, right? But you can imagine for our case, so this would be like, let's say we have 64, an action chunk of 64, right? So there's 64 tokens, and then the D will be 1024. And then you multiply this will be 1024, comma 2048. So then you get L by 2048, right? So this is 64 by 2048 for the action. And then for your for the VLM side, right? You also have L by D, but it will be like something else, right? Because you have, let's say it's like much bigger, right? Like let's say 200 by 2048, and then it'll be 2048 by 2048. So what you end up with is like, okay, you have this Q for the action will be 64 by 2048, and the other one will be like some bigger number by 2048, right? So they're the same hidden dimension now, but the L is different, right? But you can just concatenate those together, and so you end up with like concatenated values, and then you can apply attention, right? Because then you do the multiplication, Q by K, and then you end up with like LDK times DKL, right? And then you get L by L, and this L would be like L of the VLM plus L of the action, and so then you end up with, right? If you look down the image, you sort of have this, right? L by L, where the L is the image tokens, the text tokens, and then you have proprio tokens and action tokens, and you sort of get this. So that's like how it's actually implemented, and you can look at the source code if it's still confusing. But yeah, that's sort of like, I looked at the source code a little bit to try to understand this. Okay.
I have another question, sorry.
Yeah.
The VLM,
Yeah.
so do they train the LLM first and then the clip model and then put them together, or do they train them in parallel?
Yeah, I think they're trained separately. So the LLM is trained alone, and then they take a pre-trained SIGLIP. Right. So SIGLIP, SIGLIP is there's a text encoder and an image encoder, right? And again, what I was trying to explain is, you train it to contrastive loss. So the idea is like they want the image, like if an image and text are pretty close, right? After it goes to the text encoder and the image encoder, the value should be like kind of similar, right? Because they should represent the same thing. So after this gets trained via the contrastive loss, they actually won't take the text encoder. They'll only take the image encoder. And then, they'll take this pre-trained SIGLIP, pre-trained decoder, but what they need to learn is this linear projection, right? To go from, because this SIGLIP was trained independently of this was trained independently of this, so there's some gap here. So I think mainly what the update is this linear projection. I might be slightly wrong. This might be still like unfrozen during like the training, and this might be unfrozen. I'm not super sure, but my intuition is that the main thing that changes is this, right? Does that answer your question?
Yeah. Would there be any downsides to doing it in parallel and then not caring about linear projection? Other than compute, I guess.
Like if you weren't to freeze it, or you, I guess perhaps like training stability, or you want to prevent. Sometimes what happens is there'll be some unlearning, right? Like if you let all these things change at the same time, like you see this in like reinforcement learning. Actually, like I've been like doing some reinforcement learning, and there's some. I guess actually I don't have a super good answer. Perhaps I don't want to like invent stuff,
Okay.
so I don't have a If someone can answer that,
That's all good.
like if you freeze it versus not freeze it, what are the advantages? Like maybe like this is already a good representation. Like it's already a good encoder. If you let it change, like perhaps like it might get slightly worse because there's just so many parameters to change, and you might need to train it for longer for it to actually like converge to something good. That's perhaps like part of the answer. Yeah.
Don't they like kind of freeze the weights or like prevent like fast off in like 25?
In the Pond 5?
Like wasn't that the new thing?
That's you want to present 0.5 next week?
Like that's the main takeaway I got. I thought it wasn't like I didn't pick up on everything maybe, but like maybe that was the new thing they found out. Like okay, the action expert's like pretty important, but like if it like affects your pre-trained VLM, then
You're referring to Pi 0.5, right? Yeah, I think I didn't read too deep yet in that paper, but mainly what I remember is like they enable subtask prediction, right? Like for longer horizon tasks, they'll feed the VLM into the action expert better, but you're saying they're freezing it?
you're like yeah. I don't know if it's freezing exactly.
Because in Pi 0 they don't freeze the VLM, right? Yeah. Okay, one last question, and then we need Krish to present.
If you go to the slide where you had like the layers of the product,
Yeah.
so they train like the action expert, like the action chunks.
Yeah.
They do like the whole like the diffusion loss thing.
Yeah.
Right?
Yeah.
Do they do anything to like the VLM side? Do they take the outputs of that at all and like
Yeah.
those outputs? Or?
No, they don't. But I think Pi 0.5 does. So yeah, I'll just pull out Pi 0.5 quickly, and maybe we can do that for next week if people are interested. Because if you look at here, Pi 0.5. Yeah, I think somehow, I'm not sure what this is exactly doing, but it seems like, right, it goes, these are the inputs, the output is somehow used in some way, whereas in the Pi 0, yeah, it's just like, yeah, the VLM spits out tokens, like, but like it's not really looked at.
Okay,
But so,
just, like, throw out the tokens.
yeah, you could potentially look at it and like, it should spit out something like useful, right? Because like, it should understand language, right? Yeah. But yeah, I think in Pi 0.5 they do something with the output of the VLM. So we can maybe cover that next week. Okay, cool. Thank you guys. Now we're gonna have Krish. Okay. Yeah, I'll mark you up.
Oh yeah, sure.
Okay.
Actually, this is not the best way to do this. Okay. Hi, I'm Krish, by the way. You guys can call me Kesu as well. I guess like I could do a quick briefer on what I do. Basically, currently I'm working at this place while I'm building this company called Palatial, where we're trying to do like real to sim stuff, essentially creating like data pipelines for taking in real world sensor data and being able to convert it to any simulator format. And we're trying to basically do a bunch of different innovations in that regard. For example, something that we are currently working on is inferring physics from pixels and like being able to understand like the physical properties of objects and things of that sort. So pretty cool stuff. Pizza by them today. But yeah, this is what I do. So I don't come from a traditional like, well, robotics background, but more like I tinkered around in hardware. Hardware was cool. Got into robotics. Robotics was cool. Then slowly started going deeper into like everything like ancillary to robotics. So like perception, also like geometry, graphics, and those kind of things. So kind of all over the place right now, but very, very exciting. I'm so excited for our future. I low-key want to see like robots everywhere, like ASAP. But I don't think we're getting there today. So let's talk about what's going to happen in 2 years from now. This paper, I think I was very fascinated by because, oh, by the way, I also do some research at NYU right now, where I'm working with their, it's called the Grail Lab, where we are basically also doing similar stuff, but more towards evaluations. So like, how can we sort of understand the differences in evaluations between sim and real, and use that as a prior to see how to measure the sim to real gap better. So things of that sort. And a reason why I thought this paper was extremely interesting was because we started looking into like this thing that's been pushed by Russ and like the TRI team called large behavioral models. And it's been very interesting to see how like the overall architecture for these future models, like these end-to-end models, are starting to like converge almost, but like with certain differences in like data techniques and like also like, for example, like Pi uses like flow matching versus like this uses like a simple diffusion transformer. So it's like smaller things that are starting to show up as like the bigger reasons for why policies tend to act differently. But let's go deeper into the two different architectures. Is this like zoomed in?
You can zoom in more. You should zoom in.
Okay, cool. So over here, like in terms of like the general like overall high-level architectures, like you've got RGB images. One thing to note is like they did not do any depth stuff, which will be useful in the future to remember. They also had certain like language instructions generally provided as part of the entire multitask action, and then end effector poses and a diffusion time step, usually K. This K was supposed to be about 16, was supposed to predict around 16 time steps further into the future. So it basically predicted 16 actions in any given frame. And then we've got the classic VIT, which is clip-based embedding model, similar to what SIGLIP uses, but SIGLIP's more focused. And then you've got an LBM diffusion transformer, which they don't go deeper into like explaining how the diffusion transformer is set up other than this picture on the right. But generally you've got some sort, like the process is like, you have some sort of a step-by-step process of like, you create like an observation embedding, which is basically fused in together in one embedding space with vision, RGB images, language, instructions, proprioception, and effective poses, and the time step itself. And once you have these, you basically have a DIT denoising process, and then eventually you predict like the 20 next actions for the 20 degrees of freedom. And the way this works is for the next 16 actions. So that's how the entire architecture is in general for LBMs versus your Pi 0.5. You can see that there's some sort of like overlap here where it's like you have this pre-trained VLM with SIGLIP and Gemma. It's also divided into discretized actions, also language subtasks. So the only difference is how there's one extra like clever trick that Pi 0.5 uses with bounding boxes, where you basically like in your pre-training phase also create bounding boxes, and in the future when you're also inferencing, you also like predict the bounding boxes to take the actions.
Sorry to interrupt. So people booked this for 7 to 9, so we need to move somewhere.
Oh shit.
Yeah. Yeah, they have a meeting right now, so we're gonna move somewhere.
Okay.
And
I guess we'll move.
find a room now.
Yeah. Do you want to go find a room first?
Well, we need to move first because they have.
Anyways, I see.
For real world interpretation.
Yeah, I didn't want to bother you guys on that.
No, all good.
Class or something.
No, you're good. Thanks, dude.
I can carry you.
Oh, okay. I'll take the laptop.
Yeah.
Thanks, man. Yeah, that's me. Nice to meet you. What's your name? Reese?
Like the peanut butter cups.
Nice. How much more, bro?
Yeah.
No, this is too much. Okay, cool. Yeah, so generally like the embedding dimensions are 768, and the image encoder is the classic VIT B16, which is also 768. So that's how the model architecture has been set up. What this generally gives you is like, it's robust to uncertainty, and this is going to be a very important keyword for us while we look into evaluations. There's good generalization, which is something that hasn't been seen too much in like robotics models. And when I say good generalization, I mean success rates around 50%. That's good. 50. Like we'll see these values keep ranging between 50 to 80, but like generally good generalization could range anywhere between 50 to 80, and that's good.
What do you mean by generalization?
Like generalization is different lighting conditions, different objects, different textures, same task. And that task could be defined as something like pick up this red object and put it in one corner of the room, something as simple as that. So that generalization is what we tend to see with the large behavior model, which we also, like if you've been on X, then you're seeing Pi 0.5 also kind of like, people are like raving about it. But that does not mean you don't have to fine tune. So we'll go deeper into that. So yeah, there's general convergence on the style of the model, and best way to represent what is not different. What is different now is how you do data augmentations and image augmentations and like train your models, all on the data side. So generally, like this is the pre-training data set. So you've seen there's bimanual robot teleoperation that they did with 468 hours which is their biggest like the most expensive data that they collected. Simulation data also was teleoperated, but collected in simulation with 45 hours. This is fairly new because generally seeing a mix of simulation data with real data is not that common. But they found out that doing something in simulation allowed them to also eval better in simulation. And so this becomes a very important recipe for doing evaluations in simulation itself. And then UMI is a data set, so that was around 32 hours. And then Open X-Embodiment is also a data set, I think by Google. That was part of like the RT1 like generation of data sets. And then you've got a simulation software that they're using called Drake, because the guy who built it is Rusted Drake, one of the main guys in the space. Boss man. So some general like terminologies that were used in this paper that were thrown around was like co-training. So basically mixing simulation synthetic data with real data. But in this case, rather than having like scripted results for like collecting the simulation data, they had teleoperation. So that allowed, from my experience in like just simulations, what that basically means is like for the simulation environment to be well set up, you need to have really high fidelity assets that also allow the behavior is not non-deterministic. You want to make sure that the assets, when touched in the same space at every single step of the simulator, behaves the same way. And teleoperation allows us to do that if this asset quality is great. So they basically ensure that the asset quality was great, simulation fidelity was high, and so then they were able to co-train very well. Distribution shifts. Basically, like test conditions differ from training. Different lighting objects, robot stations, clutter. You can't map one-to-one, but you can come very close to it, which was like a big focus of this paper, where they were basically able to take a setting and then try to create the same setting in simulation. So that is something that you don't necessarily see in most robotics papers when doing evaluations. So that was pretty good. That basically allowed like the comparisons, like because they were able to mix simulation data in their training, they were able to eval, and because they kept one-to-one like relationship between the simulation and the real world testing, they were able to also get better results in terms of uncertainty and like knowing how strong the policy actually performs rather than having weak guarantees. So that's what they were able to do with their training setup. Ramen is basically what they call their data set. Single task. So the way they did evaluations was like with baselines between data collected for single tasks before fine-tuning and with just pre-trained data. So you'll see those baselines in the next few slides, well, images. And then fine-tuned LBM is basically pre-trained and then fine-tuned on the same small data set that was used for the single task. I think VIT is generally like image patching and embedding. So you basically have these image patches, and then you basically have a linear projection. You normalize the flattened patches to a certain degree, and then you have a transformer encoder. The encoder has like skip connections and multi-head attention to allow for like global features to be well captured, and then you have a final MLP head to give out the class. And the class token is something that's common with VITs compared to CNNs. So they found, so generally like CNNs, they are better than CNNs when trained on a lot of data because they are able to capture like global attention. Global attention. Like global features essentially between all the different parts of the patches in the images. And so Clip, I think Steven probably did a better job in terms of explaining everything. But generally you have a text and image pair, you encode them together, and you get a class. So that's how Clip works. In terms of data collection, each demo contains like all of these different like things for conditioning and creating that one observation embedding vector. And so generally like a lot of these data sets have like only like one arm performing rather than two arms performing. So what they did was they basically swapped between different arms to create that generalization. And sometimes they also did like just like zero padding, like the second arm doesn't perform any actions. So that's how they sort of try to generalize between the two arms. and they used a relative trajectory representation for poses. So what this means is like, they, rather than having like a world point view, they had camera intrinsics, and they basically used the gripper positions to understand how the camera poses kept changing, and you use the end effector poses at that point to create the training set. So imagine like you're starting from like an end goal, and you basically work your way backward to understand the entire trajectory of the movement in the relative frame of the camera. So that's how they did the representation for poses.
Oh, I didn't totally understand.
Okay, yeah, I should have created a thing for this. But like, imagine like, let's say it's a door closing task, okay? You know at point X into the future, your end effector is gonna close, right? So at point X, your end effector closes, and you know the pose that you have for your end effector at that point. And so basically you look at relative camera trajectories as the end effector starts to like revert back, and you collect your, and the starting point at that point is.
Is there a reading here?
Is this the?
We got kicked out of that.
I thought so. They told me that the whole place was booked up the whole time. Yeah.
Are we okay here? Or?
Yeah, that's fine. You guys are.
No, you should go through.
Can I go through?
Oh, yeah.
No, like, it's okay if I overlap your lines.
Oh, of course.
Okay, sounds good. I didn't realize you guys were all here. That's funny.
Right, are you back? Okay.
I thought that room was.
Are the poses relative
to the camera.
to, so you have the end, like, what does the policy see? Like, what is it trying to learn?
It's trying to learn when the end effector closes, and trying to predict the poses along which it closes. So for example, at like point X, if the gripper value is 0, and at point, like starting point is like A, you basically want to like decouple these two, and you want to start your trajectory from when the thing closes. Primarily because what if you started like 5 seconds into the future? Like for example, like for 5 seconds you did nothing, and your data has been collected, and that's going to add to the data. What?
What's that sound?
Oh, that's tea. Yeah, or water.
Ambiance.
Okay. Yeah.
I have like a follow-up to that then. Maybe I'll get to it as well. You mentioned like they don't use the depth from stereo.
Yeah.
I guess what's meant by pose here other than like gripper open close state then? Are we talking like actual like
Camera.
6th off?
Yeah. We are talking about 6th off.
6th
Correct.
off of the tool center point of the gripper.
Yes.
Okay.
Which is generally the camera frame.
How do you get that without doing like, how do you get that depth without doing like stereo vision?
Well, there is stereo vision in this case, right? Because you have 2 arms.
Right.
And so you basically do like you look at epifocal lines and like the structure from motion, and then you try to understand the camera intrinsics between the two, and that's how you basically like revert back.
Okay.
Yeah. But yeah, that's how they're like. This is just their data representation. This is basically they're predicting like poses and end effectors, and yeah, and so this allows for better generalization across stations.
This is actually extremely important. I guess I don't fully understand how to do it in this specific case, but Ross Drake also had a post on how action normalization is like really important.
Right. You'll see more on actually. Like you'll see a little less on normalization. You'll see 1 line on normalization, but it's like they said this was like their biggest like reason for having a much better boost in performance.
Because yeah, like you can imagine like let's say you do pick and place, right? And if you do pick and place like here versus like here, if you use like the global frame, it needs to learn 2 different representations.
Correct.
But if you represent it relative to the pose, like within the next 64 action chunk, like you always consider this pose as your 0.
Yeah.
Then
and then you
like have. Yeah, it needs to learn less things because these 2 cases is the same.
Right.
Is that sort of what you were saying?
Yes.
But that, okay, if that's exactly what you meant, then okay.
Yeah. It's all relative to the camera frame, and so it's looking at the poses.
Because you were saying like you just like traverse it back and then
So that's like another way of collecting this data because you know exactly where you ended rather than when you're starting.
Right.
So it's just like a data capturing technique. Yeah. You'll actually see this being used for the other paper called Robot Utility Models. It's like the same concept, which uses like a different architecture called vector quantized behavior transformers. But that's how relative trajectory representation works. In terms of data cleaning and usage, they basically had like certain heuristics where they were like, okay, so motion threshold greater than 5 centimeter translation, then you basically don't take that robot like data segment at all, and you just skip that. And then you look at, so another way they basically had like a bunch of data, rather than cleaning it, they just trained it. And that was part of the pre-training step. But for single tasks, they would basically look at the best quality data and then fine tune based on the best quality data. In terms of what is best quality, you look at noise. You look at how much sensor noise you have, signal noise you have, and you try to basically remove any that looks bad visually. So generally this is based on the person that's reviewing, but obviously there's different, like there's some bias here. Data normalization was like at each step you basically make sure that the pose and the gripper width are normalized. This is what I think Steven was talking about.
There's smoke coming out of it.
It's fire.
Guys, you gotta evacuate.
Damn dude, this paper's fire. Yeah, another thing that they did for evaluations was like they tried to really understand how much data you need to fine tune. So they tried to like basically try 15%, 30%, 50%, 100% of the data to measure data efficiency. And then they found like 3 to 5x more efficiency when you fine tuned it on a pre-trained backbone.
We know when they say fine tuning, like, so like, for example, I assume the learning rate is lower, right? Like, did they mention any like implementation details of fine tuning?
No, they did not actually. I mean, they mentioned hyperparameters for image augmentation, but that's pretty much it.
Because at what point does fine tuning just become like training? Like that's something that's what you're trying to get to, right?
At what point does fine tuning become training?
Yeah, like yeah, the learning rates. I think is it fine tuning the learning rates are just lower, so it
Generally, yeah.
Lower. The data you give it is not like as very. Although like in Pi 0, they also when they say fine tuning, they still like give it a bunch of tasks. So I'm not super sure. Like it's a very
it's thrown very the word's thrown very loosely. Like it's not like there's like no definition to like what classifies fine tuning. It's kind of like relatively speaking, I guess.
Whereas in LLM world,
it's like
LLM world, so, like when they fine tune, it's like very specific.
It's like on a specific like subset of tasks.
Yeah.
Fine tuning, sometimes they make a distinction based on like data quality. They only fine tune on
high quality
stuff that they've checked and think it's high quality.
Right. Also, like in this case, when they say fine tuning, they basically create different policies for different tasks to do the evaluations. For example, if the task is like put kiwi in center of table, right? Then they have like this single task baseline, which is the gray one. And then they have like a classic pre-trained LBM, which is the blue line. And then they have like a fine-tuned LBM, which is the red line. And what they did was basically take the data that was used for single task training with the pre-trained LBM and then fine-tune it with the single task data. So that was basically what fine-tuning for them was, to see if like, so their correlation to understand was like, does a pre-trained backbone for LBM lead to easier, like lesser requirements for fine-tuning? And like, does it make things more data efficient, and does it make things more robust? And basically that's what they found. Another thing to note is like evaluators did not have like prior knowledge of what policy was being run, which is generally like, so they had a rubric for understanding how to evaluate. So for example, if it was something like put kiwi in center of table, like they would have a rubric, which first part of the rubric was, did the gripper move to the kiwi? Second part of the rubric would be, did the gripper close on the kiwi, or did the gripper miss the kiwi? Third part of the rubric would be, did the gripper carry the kiwi? Fourth would be, did it keep it in the center of the table?
What's the point of like not telling them what policy was used? Is like so eliminate bias in evaluation?
Correct. Yeah. Okay. So for example, like so one thing I've seen is like generally like a policy trained with more checkpoints might not necessarily like mean it's the best checkpoint, right? So you want to eliminate, like, if you tell someone that, hey, this is the most trained, like this is our best policy, they are more likely to, like when evaluating on certain kinds of rubrics, they are more likely to have leeways. And you have to understand when you're evaluating in these situations, you have a lot of uncertainty. For example, like if the kiwi ends up like slipping, right? Does it mean did it grasp it or no? Like it did not carry it, but does it mean did it grasp it? So that kind of biases when you tell someone that, oh, this was our best trained model. That means, oh, maybe I should be more lenient with how I end up giving it this rubric score.
So it's human psychology. What I thought you're talking about is like, for example, like let's say there's a policy with a lot of checkpoints, then they might not test it on it being generalized that much because they'll be just testing on stuff that's been trained on in a sense, if that makes sense.
No, so it's like the policy rollouts, so the way they did like testing in general was like they have 50 to 100 like 50 to 200 different like simulation rollouts versus real world rollouts, and the conditions were like randomized across all these different rollouts with different textures, different objects, different positions, different lighting conditions. So they always tested for generalization. Okay. This was just to make sure that there was no human bias that was involved.
Okay, got it.
Yep. So other thing that was really cool over here with how they did the evaluations was like they did Wahlen plots. So what that basically means is like the wider the Wahlen plot, the more likely it is. The narrower it is, the more unlikely it is. Or like the more confident or less confident you are, or certain or uncertain you are. And yeah, so they had like large sample sizes for each sort of like task. They would do it on 50 real and 200 sim. And this was like the most important part of like how they did the entire analysis, where they had like a Bayesian analysis. What they basically did was, yeah, so they assumed that it was a Bernoulli distribution, which is like either the task succeeded or task failed for success rate. And then they assumed that they looked at each distribution of the first few simulation rollouts, and without assuming what the probability was, they accumulated simulation rollouts to finally get like a final success rate. So it was basically like, it was the harder the task, the less likely it is, like the harder the task, the easier it is to display it over here in terms of how certain or uncertain it is. And when you see A, B, and C, they basically do something called CLD, which is compact letter display, which is like, they are basically proving whether the performance of two policies was greater than 95% or not. So if they have the same letter, then they're completely sure that the policy behavior was much different. But if they have the same behavior, then they would have the same like lettering as well. So that was like, like no paper has ever done something so rigorous in terms of statistically analyzing every single aspect of this of the simulation rollouts versus real world rollouts versus performance of different policies between single task LBMs and fine-tuned LBMs. And they did it across distribution shifts and non-distribution shifts. Distribution shifts are basically varying conditions in external conditions. Factors, yeah. Yeah. So yeah, it was just not a simple like numeric saying that, oh, 65% success rate. It was more like within this distribution, it was uncertain these many number of times. And you could basically like backtrack to calculate those kind of things. One very funny thing that they did with the paper was they realized they didn't normalize everything perfectly. So there were certain batches of like the fine-tuning aspect which were normalized beyond the range that was used for the rest of the data set. And this data normalization is the same as this thing that we talked about, which is make sure that the pose and the gripper are normalized. And so yeah, they basically did all of that. And the main key takeaways from the paper for me was like fine-tune performance smoothly, like there are stats to this. I didn't mention the stats because it doesn't seem like something that really makes a difference. You want to understand the concepts. But yeah, fine-tune performance smoothly improves with increasing pre-training data. So we are very much in the AI scaling law for robotics domain, and we're still trying to figure out what the scaling is. So end-to-end models, are definitely the future, and there is a clear path to that. But right now, with what scale we have, we'll always require fine-tuning. That's what's been proved. Architecture seems to be good, but data normalization can have, for example, like they found that data normalization had larger effects on performance. And so we just need to find cleverer tricks to do data, basically. And I think, I forget the name of the guy from Berkeley, Kevin, is that his name? The professor?
Kevin from where?
Kevin, the Berkeley professor? No, there's another one. No.
Kevin.
Ken, yeah, Ken Goldberg. Like, as he puts it, like good old-fashioned engineering. He has this thing where he just like goes on a rant. Like, he's like a little bit of a doomer, so he's like, oh yeah, good old-fashioned engineering, that's all we need. But then he's kind of not wrong, but also like at the same time, it's like we have a potential to see end-to-end models in the future, so we shouldn't be relying on just good old-fashioned engineering. Throw data at the problem. And yeah, they were able to like do a lot of evals in simulation and be confident of what the performance was. And they laid down the foundation for like statistical rigor in evaluations. Yeah.
I don't understand the good old-fashioned engineering.
Oh, it's like, for example, like the bounding boxes. That's good old-fashioned engineering. Like if you just passed on the bounding boxes, like this is not for LBMs, but this is more for by 0.5. But like basically in the pre-training phase, what they would do is given a certain set of actions, and images, they would overlay bounding boxes over the affected like object in the image. So for example, if the task was put kiwi in the center of the table, they would create bounding boxes over the kiwi through every single image. And what that basically allowed to do was it led to like better feature localization for.
It's trying to predict the bounding box in addition. So it's basically like the model was forced to like predict multiple things, and how does that relate to the good old-fashioned engineering?
It's like if you could have just given the image, right, and like it wouldn't have like affected anything. Maybe like in certain cases it would be uncertain, but over here because you gave bounding boxes, they saw like an increased success rate. So it's like smaller things like that where you basically augment your data in the pre-training phase. You can have like better performances from the same architecture. So it's more on the data side rather than on the architecture of the model side. So that's like the good old-fashioned engineering bit. Over here, for them, the data normalization piece was like good old-fashioned engineering, where they basically normalized like random values of data between negative 0.5 and 0.5, and they saw better performance out of the same architecture. So yeah, that's this paper.